This is a lecture for Chapter 8, Statistics 253, on problems with hypothesis testing. In the homework for Chapter 8, you'll be given several journal articles to read that discuss hypothesis testing and some of the problems associated with it. I want you to read the articles just to become better educated about hypothesis testing, and to see that although we can do calculations and do them out to 10 decimal places, we've got to look a little bit behind what we're actually doing and not get too carried away with the mechanisms or the mechanics of doing these calculations. And this is especially important in statistics, where we're not just calculating a value, instead we're discussing results and the implications of results from a study. One of the first problems is a logical error that follows from something that Bayesian statisticians always like to point out. Okay, and this was on the first exam and in this class, and we've discussed it before. Sometimes people kind of miss the point here, so I want to go over this again. P here is standing for probability. And of course you know that this line, the vertical line, means given. And what's after it is given that whatever's after it is true or has occurred. So we're going to let D be the data or the test value or the new data that you've calculated, the new result. And H naught is the null hypothesis. Okay, when we looked at the p-value, the p-value was a probability that the data would have occurred given that the null hypothesis is valid. Okay, that's a probability that you would have achieved this data point if given that the null hypothesis is true or valid. Right. So, you can use an extreme example. If you say that cats are round, pretty much roundy shaped, and that's your null hypothesis, and you see a cat that's triangular, okay, what's the probability that you're going to see a triangular cat if your null hypothesis is that cats are round? That's going to be pretty low probability that a cat's going to look triangular. Right? However, if you saw a cat that was sort of oval, then you can say, yeah, that probability that you would see an oval cat, given that that cats are round, is very high. All right, that's sort of an absurd example, but when we look at the hypothesis testing with a normal distribution, you can sort of see it here. Let me do another bad drawing. All right, so here's my normal distribution. Forget that shouldn't have been tailed going up. All right, and here's the mean for the data, and of course the curve is determined by the standard deviation. So here's your mu naught and the standard deviation of the original study, and all this constitutes your null hypothesis, or is related to the null hypothesis. Mu equals mu naught. Okay, your test value, let's say, is right here. Okay, what's the probability you would see that test value given that all this has occurred, given that you're in this particular bell-shaped curve, is the area here, and that's fairly high probability because you are covering more of the area, or a good deal of the area of the bell-shaped curve. On the other hand, let's say that your new data value, give it a different color, is out here. Well, what's the probability of getting that data? Is fairly low. It's way out on the edge, and so this area is lower. So this part of the equation, which again this equation doesn't hold, is truly your p-value, and it makes sense. All right. Now, what does the second statement say? Okay, I'm going to have to clear this board a little bit here. Okay, the second statement is not really a problem with hypothesis testing. It's a problem with interpretation of the hypothesis testing. This statement says that what is the probability, or the probability that the null hypothesis is valid? The probability that the null hypothesis is valid given the existence of this data point. Okay, remember when we first started talking about hypothesis testing, the null hypothesis is assumed to be valid, and you're not proving or disproving it. And that's what this statement says. This statement says if I find this data point, the fact that I got this data point either proves or disproves the null hypothesis. And that's not true. They should have a not sign in it in order for it to be true. Okay, I want to give another example of this because this is important, not just in hypothesis testing, but other places as well. And like I say, it occurred on the first test, and not everybody understood it there. Okay, so let's give the example that I did in that exam. Okay. And the fact that the equal sign is crossed off makes this statement true. And let's say event A is associated with a person committing a felony. And B is a person is seen in jail. Okay. What some people missed is the fact that the P is here, and the P is the probability of this happening. So this is the probability that a person, well, I'll choose my initials, is seen in jail given that I committed a felony. Okay, what's the probability you're going to see me in jail, or that I will be in jail if I had already committed a felony? That's very high. That's a very high probability. What does this mean? This is the probability, again, the P stands for probability, that I committed a felony okay, given that I was spotted in jail. Okay, what's that probability? It's actually very low. There's many reasons a person could be in jail. They could work there, they could be visiting there, it could just be a misunderstanding, right? Of course, it's always a misunderstanding, but so there's many reasons you could be in jail besides committing a felony. So the probability that I committed a felony given that I was seen in jail is very low, and these definitely are not equal to each other. And that's what this is up here. If I have I have a null hypothesis and I find some data point, that data point is not proving or disproving my null hypothesis. This part of the equation right here is the p-value, and it says given that the null hypothesis is true, valid, what is the probability, what's the probability that this data point would have occurred? And the fact that the null hypothesis is valid is shown here graphically by the fact that you're using the bell-shaped curve associated with the null hypothesis. Then the test data just comes in, for example, maybe out here, and the probability is the area under the curve determined by the null hypothesis, or the data associated with the null hypothesis. Okay, so that's one criticism of hypothesis testing, and it's not really a problem with hypothesis testing itself. It's more of a misinterpretation or a thinking error associated with hypothesis testing, but it's not infrequent that this happens. Okay, now this is an error. Number 2 here is an error actually with the implementation of hypothesis testing, and the idea is that the null hypothesis is actually false or misleading to start with, and this is called a straw man error in arguing, or in, it's a logical error. So if you have an opponent and he has a particular position on some topic, and you distort it, or you ascribe to him another position that you could easily refute, it makes you look like the winner, but you really didn't address the issue at all, and that is a problem. And why would people do it? Because they did a lot of work getting some data, and they sure would like it to be significant. And if you get through all the work and you say, well, I guess it's just about close to what people found 5 years ago, that's really not something you're going to publish. It's not going to see a lot of publicity, and it's not going to give you a lot of glory. And if you're in academia and you have to publish, well, this might have been done out of desperation. Okay, so that's a problem with it. It has to do with the null hypothesis being actually false or misleading, and maybe the person didn't do it intentionally. Another problem with hypothesis testing is that a hallmark of physics, actual science, is repeatability. So that means if I make a discovery in physics and I publish it, and I'm sitting in one laboratory, like say Livermore, and then someone in another laboratory like Oak Ridge or Sandia or Los Alamos should be able to put together the same test setup and reproduce my results. And that's a big hallmark of truth in physics. If people can't do that, then they go back and question you very severely. Okay, how about in statistics here? If you go and resample and come up with another test value, are you going to come up to the same conclusion? Not necessarily. And so the idea of repeatability isn't real strong in hypothesis testing, and so that's an issue. The next issue is very interesting from purely mathematical standpoint, and this is the idea here is that you would think that if you had a larger and larger sample, you would get closer and closer to the truth. For example, if you wanted to know how people were going to vote in a city, if you sampled everybody in the city, you probably come up with how the vote's going to go. If you get a small sample, you have to, of course, really work to make sure it's representative. That's just in gathering information or doing a study. But when it comes to this hypothesis testing, the larger the sample, the more likely that the null hypothesis will be rejected. It's not saying anything about its validity, it just has to do with the math. So let's look at the math. Okay, let's say that we have this is our original data, so we'll say our null hypothesis is that the mean equals 100. Okay, now I have an alternative hypothesis. It can be right or left, it doesn't matter. Let's just say it's a right tail test. The mean is greater than 100 because I came up with a test value of 100.5. Well, if you look at 100.5 and a standard deviation of 5, this is really, really close to 100. I mean, it's within one standard deviation, well within one standard deviation. You think that's not going to be too significant. But let's find the z-value associated with it, and then we'll go find the p-value using r. So here's your z-value. It's theta minus theta naught divided by the standard deviation of the population, in this case 5, over the square root, and we'll use a sample size of 50. My z-value is 0.707. Now what if I increase the sample size to 500? This changes the z-value because I'm dividing, actually I'm multiplying, if you work this out in a different way, by the square root of n. See how it appears in this equation? So here's my n right here, n of 500. I take its, I do the same calculation, all the other numbers stay the same, I end up with 2.236. Okay, let's go look at the p-values in R associated with those two numbers. Okay, so here I am in R, and I'm going to find a p-value, and we're assuming a normal distribution, but we already have the z-value, and the z-value is 0.707. So p norm, and because I'm using z-values, all I have to do is, I don't have to specify standard deviation or the mean, so it's 0.707, and it's a right tail test, so I'll set lower dot tail equal to false. Okay, I did it like that, but now I have to type this to get, okay, this p-value is 0.2397. Oh, that's humongous, right? Because, okay, a p-value of 0.10 is associated with a confidence level of 90%. A p-value of 0.05 is associated with a confidence level of 95%. This is 0.239. This is about, I mean, you have absolutely no confidence, okay, at all here, okay? So as the p-value goes up, its confidence, I shouldn't use V for value, just confidence, is going down. Alright, now let's do the same thing. Remember, nothing's changed, but now we have a sample size of 500. And we'll again compute the same p-value. Oops. To get back to my cursor. Okay, I'll do exactly the same thing, but I'm going to put in here, it was 2.236. This is for the sample size of 500. Turn it off. Here's my p-value, 0.012. That's pretty close to a 90% confidence level. Alright, I can repeat that calculation again, and this time I'll do it with a sample size of 1,000. So here's my z-value is calculated like this. So z is, my test measurement was 100.5, my original mean was 100, or the mean of my test value. Okay, and I divide by the standard deviation, which was 5, divided by the square root, and now I'll use 1,000, and I come up with 3.1622. Okay, that's going to get erased, but let's go find the z-value for that case. I have to erase it in order to get the cursor back here. Okay, so I'm doing exactly the same thing again, except now my z-value is larger, and let's see what that p-value is. Very, very, very small. So this was that principle that was cited in as one of the problems with hypothesis testing, is that a large sample will disprove any null hypothesis, whether it is valid or not. And here is the final kind of quote-unquote problem with hypothesis testing. Although we've mentioned some things here, and the papers that you're going to be reading for this chapter will mention other problems with hypothesis testing, there is no easy fix, and there's no easy replacement for hypothesis testing. In other words, it's still going to be around, and you still need to use it, but it's just good to know its limitations, or be aware of some of its limitations.